Okay, Assalamu alaikum. So this is week number 10, which is the last week for module number 3. In this week, we are going to discuss the part 2 of the reduced instruction set computer. In particular, we are going to discuss the data hazards that may happen in this computer and how we can avoid them. So first of all, the throughput of the pipeline is reduced by the maximum level available. So basically, filling up and emptying the pipeline will give us some reduction in the throughput of the pipeline. The second part is the data and control hazards that may occur. Of course, structural hazard is not possible in our pipeline. Why? Because because in our pipeline, if I can go just immediately here, we have the data and the instruction memories are separated, so we will not have the problem of having data hazard. So the hazards that we are going to talk about, so structural hazard, sorry. So the hazards that we are going to talk about are basically data hazard and structural hazard. So hazards are timing problems that rise because of the execution of the operation in the pipeline is delayed by one or more cycle from the time of the execution of the instruction. If a subsequent instruction tries to use the result before if it is presented in the register file, then we are going to have a data hazard, as we said earlier. So the two solutions for these problems are basically a software solution and a hardware solution. So for instance, consider the program where we have move A, R5 to R1, and then we are going to add R6 plus R1, put the result into R2. Then we are going to read R2 and R1 and put the result into R3. So in the execution diagram over here, you can see that the write back of R1 is done in cycle number 4, whereas in cycle number 3, we want the value of R1. So over here we have a data hazard because we want to read a value which is not presented. Now in cycle number 4, since our data path is presented with a register file that can read and write in the same cycle, so in the first cycle we write, in the second cycle we read, we don't have any problem. We also have a data hazard between R2 and R2 over here. So R2 will be written here and we want to read it over here, so we have a problem. Now the software solution is basically quite straightforward, where we are going to basically insert an op instruction after each instruction that has a hazard. So this is done by the compiler. So we have an op instruction here, we have an op instruction here. This will delay our pipeline by one clock cycle, and this one clock cycle is enough to make sure that we avoid the data hazard. Now this solution will increase the execution time of our program from 6 cycles into 7 cycles, and into 8 cycles, because we have to we added 2 instructions. As you can see here, we have avoided the hazards. We have the write back and decode operand fetch. Remember, the write back and decode operand fetch in the same cycle, we have no problem, because we write into R1 and we read into R1. So first we write, in the first half cycle we write, in the second half cycle we are going to read, so in our register file. So this is no problem. Now the data hazard software solution, the compiler or the programmer generates a machine code to delay the instructions so that the new values are available. So the program is written in such a way that any pending write to a register occurs in the same or earlier clock cycle than a subsequent from a read of that register. To accomplish this, the programmer or compiler, usually now the compiler, needs to have detailed information of how the pipeline operates. So figure B illustrates, this is figure B, illustrates the whole operation of having the NOP instructions. This is done as a software solution. We add the NOP instruction to our register file. Now, at worst, this approach has writes and subsequent reads in the same clock cycle. This indicates as the pair of consisting of register write and subsequent register reads connected back to back in the diagram, in the diagram. Because the read is after the write is accomplished in this register file, the timing shows that this is no problem. So the backdraws of these methods are two drawbacks. First of all, the program is obviously longer, although it may be possible to place other unrelated instructions instead of the NOP instruction. The program takes 2 clock cycles longer and reduces the throughput by 0.5 instructions per cycle by adding these NOPs instructions. So we added 2 instructions which will decrease our throughput. Now, instead of the programmer or the compiler pulling NOPs in the program, we need to do it automatically using the hardware solution. Now, with the hardware solution, we want to do all of this automatically. So in order to do this, when an operand is found in the decode operand fetch stage that has not been written back yet and associated to the execution and write back of the stalling of the instruction fetch or decode operand fetch in one cycle, then the flow resumes with the computation of the instruction when the operand becomes available. Okay, so this is done through figure 3.6. So we fill up with bubbles. These are called bubbles. We fill the pipeline with bubbles. So when we detect that we need an operand that which is not already written back, we redo the instruction. See, the instruction is done twice. This is done through bubbles. This is a hardware solution. It is similar to the NOP solution, but this is a hardware solution. So once more, it says when the operand is found at the decode operand fetch stage that has not been written back yet, and associated execution and write back are delayed by stalling the pipeline. Now the instruction fetch and decode operand fetch in one cycle. Stalling the pipeline is done by inserting a bubble into the pipeline. Then the flow will resume as usual. Now, how do we do this? Okay, how do we do this? So figure 6.3 shows that when the flow for the add instruction is prevented beyond the decode operand fetch, the next 2 clock cycles are bubbles passed through the execution and write back stages, respectively. The holding of the pipeline flow in the instruction fetch and decode operand fetch stage delays the micro operations by 1 cycle. In the figure, this delays is presented as 2 diagonal blue lines, as you can see over here. This is the delay. These are the delays that are presented. And you can see that this in turns will delay the full operation by a certain amount of time. Now, to implement this delay, we are going to use this pipeline. Okay, so first of all, let me highlight the parts that are involved over here. So this is the data hazard selection. Okay, we have hazard A, hazard B, as you can see over here. I'm going to discuss about them. This is the implementation of the bubbles. Okay, this is the implementation of the bubbles. You see all of this yellow part is the implementation of the bubbles in the register file. So first of all, let's talk about detecting the hazard. In order to detect the hazard, we need to satisfy the following equations. So an implementation of the data hazard handling for the pipeline is shown. The added modified hardware is shown. For this particular pipeline stage, the arrangement of the data hazard will occur in the register file if there is a destination register that at the execution stage that is presented in the write back stage of the next cycle in the decode operand fetch stage. So this is done how it is. So data hazard detection is equal to hazard A or hazard B. This is an OR operation. Now, hazard A, if MA max A is equal to 0, so this is 0 complement, which is 1. In the decode operand fetch stage, if MA, which is this one, is equal to 0, meaning I'm going to read from bus A, and this is an AND operation. destination address in the execution stage is equal to AA in the decode operand fetch stage. Destination address in AA, let me clear here to show you. Okay, destination address in AA, which is this one, is equal, okay, destination address in AA is equal to the DA. You see here, this is DA going here, and going here, and going here. Okay, and the destination address of AA are equal, and WR in the execution stage is equal to 1. So this is 1, this is 1. And we need to make sure that sigma I from I is equal to 0 till 4 for DAAX is not equal to 0, meaning I'm not writing to the register file, then we have an error. Now, how is this implemented in the circuit? Let me show you once more over here. Let me clear the circuit. So first of all, this is AA. AA has an AND gate. The first instruction in the AND gate says what? The first instruction in the AND gate says MA if the decode operand fetch stage is equal to 0 inverted. So this is my MA. This is MA, you see the red line here. This is MA going into an inverter, then going to the AND gate. The second option is having AA, which is this one, with DA, which is this one, in a comparator, having the output of the comparator equal to HA. Now, if the comparator is giving 1, then you have 1 here, and you have 1 from MA. The third option is RW in the execution stage is equal to 1. Where is RW? This is our RW. RW in the execution stage is equal to 1. And finally, the destination address DA ORed over here, entered to an OR gate, is equal to 1. Meaning all the bits of the destination address, at least one of them is equal to 1, so they are not equal to 0. This means that we are not writing back to R0. This means that we have a data hazard for A, and this is data hazard for B. The same applies over here. So this is HA, and this is HB. All of these are logical operations. If one of them happen, then we have a data hazard. So in the next part, I'm going to talk how we are going to avoid this data hazard, and then how we are going to apply the forwarding solution.